Hey Royals, in today's lesson we are going to look at sound interference. So over the past couple days we've been looking at interference of waves and we've been studying mostly on transverse waves. Now one thing we need to remember is that sound is a longitudinal wave. So it's going to have regions of compressions and rarefactions. When we have two compressions coming together, the amplitudes of the wave will actually increase as well. So the wave will get louder. Also, if we have two areas of rarefactions meeting each other, you get an area where the amplitudes will again increase and again the sound will get louder. However, if you have a compression meeting a rarefaction, that's like a crest meeting a trough, the two will actually negate each other and the sound will actually get quieter. So you have destructive interference. Now there's a couple ways that I can demonstrate this to you, and I've written a couple on the page here and we'll go through each of them. A tuning fork, like this one here, is an apparatus that it oscillates at a certain frequency when it's struck. And this frequency is going to be picked up by our ears. And it is tuned so that these will oscillate. This one here oscillates at 256 hertz or 256 vibrations per second. Now my camera can't do slow-mo, so you won't be able to see the oscillations of this tuning fork as it goes back and forth. However, what I can do is I'll show you a simulation of a tuning fork. So in this simulation, you have a tuning fork right in the middle of the screen there. And let's get it to start oscillating. So we'll give it a frequency here. And as it oscillates, you can see that it's moving the air molecules around it. And they're moving back and forth in longitudinal waves. And this causes areas of compression and rarefaction. Now the air molecules, as they come into your ear, are going to transfer that energy to your eardrum. And you'll hear it, just like if I bang this on the desk. You now hear that humming of the tuning fork at 256 hertz. Interesting fact about tuning forks is that the square on the end, at the corners, they get destructive interference. And so what I'll do is I'll strike it on the desk again and I'll bring it near the microphone and I'll rotate it like this. And you should hear areas where you get constructive interference and destructive interference. So here we go. Did you hear it? You should have heard wow, 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 wow as the sound gets louder and quieter with constructive interference and destructive interference. Now, the second way that I can demonstrate constructive interference and destructive interference actually requires an experience that you've seen in your life, and it involves a concert. So I'll bring up the image again. Here we go. So in this image on the right-hand side of our page, it has two speakers that are emitting the same frequency of sound. And if you walk across them, just like if you walked across the length of our classroom, and I have those two speakers up at the front of the room, and I played a noise, you would hear loud areas and quiet areas. It almost sounds like I'm changing the volume on the speakers. And how this actually works is that you have constructive interference and destructive interference caused by the sound from each individual speaker. So I have a picture here to show you what I mean by this. So in this picture, we have our two speakers and they're emitting the sound. So there's areas of compression and areas of rarefaction. Now the distance from each speaker is going to depend on where you're standing. So if I'm standing at this location right here, I happen to be at an area of constructive interference because the compression from this left speaker is going to meet a compression from the right speaker. And we know when two compressions come together, you get constructive interference. So the sound is going to sound a lot louder at that spot. However, if I were to stand at, say, this location right here, I would hear a very quiet noise or maybe even no noise at all. And that's because that's an area of destructive interference. I have a compression caused by this first speaker on the left, meeting a rarefaction caused by the speaker on the right, and that causes us to have destructive interference. So if you wanted to go to a concert and experience this, go right ahead. However, where you're sitting really depends on the type of noise that you hear. And so picking that ticket or that seat at a concert is very, very important for the amount of noise that you will actually experience. So the last example of constructive and destructive interference that we might hear with sound is an idea known as beats. Now, if I have two different, say, tuning forks, and one emits a frequency that has 10 compressions every second, and the other one emits a frequency of, say, 13 compressions every second, there's going to be a sound that you hear, and it's going to go wow, 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 wow. And this is known as beats. And it occurs when the compressions from each of these different frequencies meet up. And that will cause an area where we have a large amplitude. And each of these points where the compressions meet up, the noise will sound like it gets a lot louder. But there will be a region where a compression, like this one right here, meets a rarefaction of the one of the other frequency. And that causes destructive interference. So a node, and that occurs a couple times throughout this period of time. And so if we connect these dots right now, and we'll do so, you should see that the sound goes from a loud point to a quiet point, back to a loud point, to a quiet point, back to a loud point, to a quiet point, and again at a loud point. And this is the idea of beats. So I have another simulation to show you how beats actually come about and show you the wave pattern that you can observe. So this simulation has two frequencies. One on the left is 100 hertz, and the one on the right is also 100 hertz. And so if I tap this one and cause it to vibrate, you can see its wave pattern here on the bottom. So we'll zoom in, we'll see that, yeah, sure enough, there it is. That's the wave pattern of the wave box or the tuning fork on the left. Now, if I turn that one off and I turn the other one on, you should notice that it looks pretty much the same. So when I add the two of them together, both at 100 hertz, you should see that the overall wave gets larger. So the red one here is the one on the left. It has no amplitude at all. So once I bring it in, there's its amplitude. It adds with the one on the right, and it causes a louder noise. Now, this is fine because it will create the same pattern for both tuning forks. And so you should just experience a louder noise in general. However, what happens when, say, the one on the left is slightly off? Let's put it at 108 hertz. So you'll see immediately right now that the amplitude goes from large down to basically zero, destructive, back up to large. Well, why is that occurring? Well, it's because if we zoom in here, we'll leave it at 32x, you see that the wave crests at this point here are almost identical. However, as we move towards the right, the crests seem to get further apart, and that's because their wavelengths are different, or their frequencies are different. And if we zoom out to exactly 1 second, you'll notice that there is 8 full wavelengths occurring in 1 second. So here we go, let's count them. Up to this point would be 1 full wavelength. There's another full wavelength, 2, 3, 4, 5, 6, 7, and this last one here making 8. So we have 8 full wavelengths in this period of 1 second. Now that would, to us, we would hear 8 loud and quiet points in 1 second. So you'd hear of the difference between these two tuning forks. Now, where does that 8 come from? Well, you'll see here that the difference between the frequencies is 8 hertz. Now, let's go back to our lesson and see the algebraic expression to explain what's going on here. So in that simulation, I showed you that there was 8 beats per second, and it was a difference between the two tuning forks. So on our page here, you see that the frequency of the beats that we hear with our ear is equal to the absolute value of the difference in the frequencies of the two tuning forks, or two sounds. Now, I'm using the absolute value because who told me that the left box on that simulation had to be the 108? Could it have been the one on the right? And the answer is yes. The difference between the frequencies just simply had to be 8. And we would have still experienced 8 beats per second. Now, this idea is very important for musicians. If they're trying to tune their instrument, they have, say, a tuning fork here, and they'll bang the tuning fork at a specific note. And they'll play their instrument at what they think is the same note. And if you hear beats, it means that the instrument is actually tuned incorrectly. And the number of beats tells you how much you need to adjust your instrument so that it is in tune. Now, people with good musical ears can actually go to an orchestra and pick out single instruments that are out of tune based off of the number of beats that they hear. Now, let's do a sample problem that uses this idea of beats. In this sample problem, we have a tuning fork, and we know its frequency is 256 hertz. We have another tuning fork that we're not really sure what frequency it emits. But when they are struck together, we hear beats of frequency 5 hertz. So that means we hear 5 oscillations every second. Okay, so that allows us to find out what the second tuning fork might be. It doesn't tell us exactly what it is because we'll have to do another small part of an experiment, which is the second part of this question, to determine exactly what the frequency of that tuning fork actually is. So for this problem, let's look at the beats. So we'll say that the beats is equal to F1 minus F2 absolute value. So we heard 5 hertz as our beats when the two of them were struck. And the first one we knew was 256 hertz. The second one, we weren't really sure what it was, so we'll leave it as F2. Right? So we know that the frequency difference is 5. It doesn't tell us that F2 is smaller by 5 or that it's bigger than by 5. It just says that the difference between the two is 5. So that means that the frequency difference might be plus 5 hertz or minus 5 hertz. So I'm going to say plus or minus 5 hertz is equal to 256 hertz minus F2. If we isolate for F2, I'm going to find out that it's 256 hertz plus or minus 5.0 hertz, which tells me that F2 is either 251 hertz or that it's 261 hertz. Up to this point, I don't know exactly which of those two it is because I would experience 5 beats with either of those tuning forks. But what we can do is we can add a little bit of mass to our unknown tuning fork and try the experiment again. So we'll have the two of them and we'll strike them together and notice that there's a difference in beats. So this was the first step. The second step, what we might be able to do is strike them. So we find out that when we did that, we get 7 hertz. And we know that when we add mass to our tuning fork, it should lower the frequency. And that's because it's a heavier tuning fork and it's going to oscillate slower. And so when we do this analysis again, we should be able to quickly identify if it's the 251 hertz or if it's the 261 hertz frequencies. So let's try this experiment again. So we know that the original tuning fork was still 256 hertz. And this is going to allow us to try to identify what exactly could be the second tuning fork. So we'll say FB is equal to the absolute value of F1 minus F2. So that gives us 7 hertz is equal to 256 hertz minus F2. Now again, because we heard 7 hertz doesn't mean that tuning fork 2 is a higher frequency or a lower frequency. It just means that it's off by 7 hertz compared to that first tuning fork. So I'm going to say plus or minus 7 hertz is equal to 256 hertz minus F2. Now isolate for F2 again. We get F2 is equal to 256 hertz plus or minus 7 hertz. And so when we do that, we get that F2 is either 249 hertz or that F2 is 263 hertz. Now, immediately this tells us exactly what that second tuning fork had to be. Because if we were to look at this answer here, 263, that means that the frequency had to go up by adding that mass, which is not possible. So I'm going to put here not possible, since F should go down with added mass. So this is possible because if we look at it, originally we thought that it might be 251. And by adding the mass, it went down to 249, which makes sense. By adding mass, the frequency would go down. So this allows us to say, therefore, tuning fork 2 must have a frequency of 251 hertz. Okay, so in this lesson, we looked at sound interference. We looked at tuning forks and how tuning forks actually in themselves have constructive and destructive interference. We looked at how you can actually simulate constructive and destructive interference with speakers at a concert or in a classroom. And then we looked at the difference between two tuning forks or two sounds and how you can get constructive and destructive interference known as beats produced by two different noises or musical instruments. Okay, so if you have any questions or concerns about this lesson, please don't hesitate to reach out to me.